Okay, Precalc lesson 3.5 on exponential and logarithmic models. So here I've got some typical shapes of graphs. The first one is our f of x equals a e to the bx, and a and b are just numbers. And in this case, b is greater than 0. We call it an exponential growth curve. Next one is exponential decay. It's f of x is a e to the minus bx, and we still have b is greater than 0. So that gives us a decay. Third one is a Gaussian model, also known as the bell curve. Here's the equation of a bell curve where a, b, and c are all numbers. And our last curve, we have a natural log, and the formula is a plus b log x. So let's look at some examples. The first one we have is an exponential growth model. And we have a city. The population is, we're going to call it P. And it's in 1996, the population is given as P of t. So population is a function of time. 95,000 e to the 0.055 t. And since this is in 1996, we're calling t equals 0, the year 1996. And the question is, when will the population reach 150,000? Well, if we were just to find p of 0, put in t equals 0, this gives us 95,000 e to the 0. E to the 0 is just 1, so this tells us what our starting population is in 1996. It's 95,000. So we have our equation. So the 150,000, this is p of t. So we'll say 150,000 is equal to 95,000 e to the 0.055 t. That's what we need to solve for t. Well, this is an exponential equation. So the way you solve an exponential equation is you take the log of both sides. We're going to use the natural log because we're using the base of the natural log e in this case. So we're going to say log of 15,000. Actually, what we're going to do first, we're going to simplify it a little bit. So we're going to divide both sides by 95,000. And that gives us 150 over 95. So that makes the math a little bit easier. So the log of 150 over 95 is equal to the log of e to the 0.055 t. So the 0.005 t comes in front of the log, like that, and the log of e is 1. So we have the log of 150 over 95 is equal to 0.055 t. So then, solving for t, up here where I have some room. So t is equal to log of 150 over 95 divided by 0.055. And that gives roughly 8.3, this is years. So to answer the question, when will the population reach 150,000? We just added to the year 1996 plus 8.3, and that's going to happen sometime in the year 2004. Okay, the next example, population growth of fruit flies. And we're saying it's given that this is an exponential growth. And so the problem is we're starting with 2 flies, and this would be 1 male and 1 female for obvious reasons. And the population after 2 days is given as 125 flies. And then after 4 days, it's 350 flies. And we want to know what will be the population after 6 days. So what we're looking for is P of 6. And so the given conditions we have, after 2 days, it's 125. So that means P of 2 is equal to 125. After 4 days, the population is 350, so P of 4 equals 350. And now we have to put this into a formula so we can calculate the, first figure out the formula, and then we can figure out what P of 6 is. So the formula that we're going to use, it's a population growth formula, is in the form y is equal to AE to the BT. And so plugging in the first data point, or our P of 2, so this is equal to P of T is the P of 2, so we can say that 125 is equal to A E to the 2B. And we have to solve for A, and we have to solve for B. So we have two unknowns, and so we need another equation. Well, our other equation is 350 is equal to A E to the 4B. And so what we're going to do is solve one of these in terms of the other. So how do we go about doing that? Well, let's solve the first one for A. So we have 125 is equal to A e to the 2B. So divide both sides by e to the 2B, and we have A is equal to 125 divided by e to the 2B. So that's A, and we're now going to take and substitute this value in for A on the second one. So that's going to give us 350 is equal to A, which is 125 over e to the 2B, e to the 4B. So let's pull the 125 out. So this is, okay, we'll rewrite it. So this is equal to 125, and then we have e to the 4B divided by e to the 2B. Well, e to the 4B divided by e to the 2B is just e to the 2B. So we have 350 is equal to 125 e to the 2B, and now we can solve for B. So solving this for B, we're going to first divide by 125. So 350 divided by 125 is equal to e to the 2B. And now we want to log both sides because this is an exponential. So we go log of 350 over 125 equals log e to the 2B. And now we can take the 2B and move it in front. And so we have log of 350 over 125 equals 2B, and the log of e just is 1, so we don't have to write that. And finally, we can write B is equal to log of 350 over 125 and divided by 2, and that turns out to be 0.51. So now we're going to solve for A. So we can say A is equal to 125 over e to the 2B. And where did we get that? Well, that was from up here. So filling in the numbers, this is equal to 125 over e to the 2 times 0.51, and that gives 44.6. So finally, we go back to our original equation. P is equal to A, which is 44.6, E to the BT, which is 0.51 T. And this is P of T. So if we want it after 6 days, so P of 6 is equal to 44.6 E to the 0.51 times 6, and that gives us a value of roughly 952 fruit flies after 6 days. So these guys have been busy. Okay, there's another type of growth model. It's called logistic growth model. And it's given by this equation here. This is a general equation where y is the population and x is the time. And this is a graph that starts off exponentially, but because of conditions, it will reach a maximum. So it will go something like this, but then it closes and starts hitting a maximum amount. And the reason for this is because either there's not enough land for the population to grow. For example, let's say we had a cage full, well, not full, let's say we had a cage that had a handful of mice in it. And you gave them a lot of food and they would continue to grow, and more mice would come. And at some point, so that's at this point here, at some point, either you don't have enough food for the mice or they start eating each other or something where it starts to level off, and so it won't grow any higher. Well, an example we have for that is a college that has 7,500 students, and a student came back from vacation infected with the flu virus, and he starts infecting other students because he was contagious. And this follows a logistic growth model. And here's the equation that we're going to be using. Y is equal to 7,500 over 1 plus 7,499 e to the negative 0.9x, and t is greater than 0. So the school is going to be closed down when 30% of the population is infected. And we want to find out two things. A, how many students will be infected after 4 days? And B, how long is it going to take until the school is closed? So for A, we're going to use the equation y is equal to 7,500 over 1 plus 7,499 e to the negative 0.9, but x, which is our time, is going to be 4 days. So you just plug that, this is all under here. So you just plug that into your calculator and you get roughly 36 students. And will be infected after 4 days. The second part, how long until the school is closed? Well, the school is closed when 30% are infected. So this problem, y, is going to be 30% of the total population, which is 7,500. That's our y. And so that's equal to 7,500 over 1 plus 7,499 e to the negative 0.9. And here we're trying to find x. And so we need to get the exponential by itself. So let's start rearranging. So I'm going to take and divide both sides by that and multiply both sides by the denominator here. So I'm going to have 1 plus 7,499 e to the negative 0.9x is equal to 7,500 divided by 7,500 times 0.3. Okay, so now I'm going to subtract 1 from both sides, so I'll get rid of that, minus 1. And let me simplify things a little bit before I go on. So the 7,500s cancel. I have 1 over 0.3, which is 10 thirds. 10 thirds minus 1 is 7 thirds. So this whole thing becomes 7 thirds. So that'll simplify things a little bit. So on the left-hand side, we have 7499 e to the negative 0.9x is equal to 7 thirds. So we're going to divide both sides by 7499. Cancel that out. 7499. And now we have e to the negative 0.9x is equal to this whole thing, 7 thirds over 7499. Okay, so here's an exponential. We're going to take the log of both sides. So take the log and log. And then we know that this goes away, so we have negative 0.9x is equal to log of 7 thirds divided by 7499. And then to find x, we're going to divide both sides by negative 0.9 and divide by negative 0.9. And that's all we have to do, solve that for x. Put that in your calculator, and it turns out to be roughly 9 days. Now the numerator is going to be negative. The log of a number less than 1 is going to be negative, and that cancels out this negative, so that's how we get a positive answer. So after 9 days, school's going to shut down because 30% of the population will be infected. So the last problem we have is an earthquake example. These are modeled by log equations. And so R is equal to the log, common log, of I over I sub 0. And where R is equal to the magnitude, and I is equal to the intensity. Intensity is essentially the energy that the earthquake has. I0 is just say it's 1, which is a minimum intensity number. It's just used for a comparison. So it's a minimum intensity number. And so whenever we have an earthquake, you hear people say, well, it's a magnitude 3 or a magnitude 4. And these are on the Richter scale. That's why they use the R to identify it. And so a earthquake with a magnitude of 3 or 3.5, it's not really a big deal. When you start getting into magnitudes of 6 or 7 or even 8, then it becomes a bigger deal. So let's take an example of an earthquake that has a magnitude of 8 and see what the intensity is. So we're going to use so that's the 8 is going to be R. So we have 8 equals log I over I sub 0, which is just 1. So we have a log equation. So to solve this, we have to exponentiate both sides, but the base of the common log is 10. So we have to use 10 to the 8 is equal to 10 to the log I. When we do that, we have 10 to the 8th is equal to, so this becomes just 1, 10 to the log 10 of I, but the I comes down in front. So this is just 10 to the 8th is equal to I, so that's the intensity. 10 to the 8th, 1 times 10 to the 8th, is a pretty big number. Well, let's compare it to a different number. Let's say we had a magnitude of 6.5. And we'll see what that does to the intensity. Well, using the same equation, we have 6.5 equals log of I. So this gives 10 to the 6.5 is equal to I. Well, that's a big difference. This is going to be 10 to the 6.5 is 3.2 times 10 to the 6th. Compare that to 1 times 10 to the 8th, and it has, the magnitude is, well, you can see the difference in the magnitude, huge. And so just because, well, let's take another example. Let's say that the magnitude of a earthquake is 9, and we're going to compare that to the magnitude of 8. You do the calculations on it, and it is 32 times the energy of magnitude 8. So that's the difference in energy, and that's what really breaks things in a earthquake, is the amount of energy that's released. So magnitude 9 has 32 times the amount of energy as magnitude 8. Okay, so that's enough examples with in 3.5, and so we'll take it from there.